Hi, today we're going to be talking about different units of concentration. At this point in your chemistry career, you've probably used molarity a lot, and so I'm not going to spend a lot of time on it today. Just remember that molarity is the number of moles in a particular volume, specifically moles of solute divided by the volume of solution in liters. Our second concentration unit is molality. And I know a lot of people get these mixed up because it looks so much like molarity, but they are different units and they're used for different things. Molality is defined as the number of moles of solute divided by mass of solvent in kilograms. So let's compare this to the definition of molarity. And you can see that they both start out with moles of solute on the numerator. So in that sense, they are alike. But molarity has the volume of solution in liters, and keep in mind that's the entire solution. Molality doesn't have the mass of solution in the denominator, it has the mass of the solvent only. So this is the second critical difference, is that we're not just dividing by mass, we're dividing by mass of a portion of the solution, just the solvent, whereas in the molarity, we're dividing by the volume of the entire solution, both solvent and solute. The reason we want to use molality is that as you get to temperature extremes in a solvent, your volume actually starts to change. So when you're getting close to the boiling point or when you're approaching the freezing point, anytime you've got a phase transition coming up, your volume is going to start to change. And that's a problem because what that means, remember, molarity, you're dividing by the volume of solution. If your volume is changing, that means your molarity is changing. Even without adding any extra solvent or extra solute, your molarity can change just by changing the temperature. So when we're doing calculations near one of those temperature extremes, we're going to use molality, and you'll see that coming up in our colligative properties lectures. So when you're asked to calculate molality, you're going to be basing it on things that you can measure in lab. In this particular case, we're looking at the molality of a sucrose solution. And to calculate molality, you need the moles of solute, but there's no such thing as a molometer. So of course, we can only base this on something we can measure. In this case, the mass of sucrose. And then we're going to convert that to moles using the molar mass. The denominator has the mass of solvent, and luckily that is something we can easily measure. And you can see we've got that number here. So here we have 122 grams of sucrose. Let's use the molar mass to convert that to numbers of moles. We get 0.356 moles. And we need to divide that by the mass of solvent in kilograms. We have a mass of solvent, it's not in kilograms, and you can convert it one of two ways. You can actually do the unit conversion method, and that gives you 0.587 kilograms of water. The way that I do it is I basically start with 587 grams of water and I scooch the decimal point over 3 places. So you can only do that if you know which direction to move the decimal point. I'm very comfortable with those conversions because I've used them a lot and also lived in Europe when I was a kid. So if you know how to do it that way, cool, do it in your head. If you're not certain, make sure that you do it the unit conversion way until you're comfortable with which direction to move your decimal place. So let's plug those numbers then into our molality equation and run it through the calculator, and here's what we get, 0.606 molal. Now you can see that the unit for this is small m as opposed to the capital M that we use for molarity. Our third concentration unit is the mole fraction. Mole fraction basically looks at the number of moles of the component you're interested in and tells what fraction of the total number of moles it is. And this is really useful when we're talking about things where you're not 100% sure which is the solvent or which is the solute. So we use this a lot, especially when we're talking about mixtures of different liquids. Here is an equation that X subscript A is the mole fraction of component A. This is a generic equation, and so I'm just throwing in random letters for the subscripts. But normally what we put in for that subscript is the actual name. So if you want to find out the mole fraction of water, it will be X subscript water, okay? And essentially what you're going to do you're going to find the number of moles of that component that you're interested in, and you're going to divide by the total number of moles. So you have to find the number of moles for every single component of your solution and add those all up. Let's do a couple of quick practice problems. Here we have a solution of 10 moles of ethanol and 20 moles of water. What is the mole fraction of ethanol? So here's our generic equation. Let's replace that with something that is not generic, that is very specific, where our mole fraction of ethanol is going to be the number of moles of ethanol divided by the total number of moles in the solution. What is that? It's the number of moles of ethanol plus the number of moles of water. Now let's actually plug numbers in for those numbers of moles. The mole fraction of ethanol is going to be 10 moles, the number of moles of ethanol, divided by the total number of moles, which is 10 moles plus 20 moles. And run that through your calculator. You get 0.333. Let's take the same system and let's calculate the mole fraction of water. And I'm doing this because I want to show you something. Again, let's take this generic equation and let's make it specific. So we have the mole fraction of water being the number of moles of water divided by the total number of moles in the solution. So now we have 20 moles divided by 10 plus 20 moles. And run that through that calculator and you get 0.667. Now there's another way you can calculate this, because when you add up all the mole fractions of the components of your solution, those all have to add up to 1, right? That's 100% of your solution. So the other way we could have done this, the easier way, is just to say, well, I know what the mole fraction of ethanol is, so the mole fraction of water is going to be 1 minus the mole fraction of ethanol, 0.333, and that's going to be 0.667. You get the same answer either way. All right, now let's do a slightly more complicated thing, and just so you know, we can keep scaling this up forever. We can keep throwing things into our solution. Here we have a solution that's made up of water, acetone, and toluene. And we want to find the mole fraction of acetone. So generic equation, let's make it personalized for our situation. The mole fraction of acetone is going to be the number of moles of acetone divided by the total number of moles in solution, which is going to be the number of moles of water plus the number of moles of acetone plus the number of moles of toluene. So we can plug the numbers in: 15 moles of acetone, 10 moles of water, 25 moles of toluene, and that's 0.3. Now we're on to our final concentration unit, which is mass percent. Now you will see this written a number of ways. Weight per weight is something that gets thrown on, for example, chemical bottles a lot. It's also called percentage by mass. And we're going to define it with this equation. The mass percent is going to be the mass of component divided by the total mass of solution. It's kind of like our mole fraction. This is going to be the mass fraction, except now we're going to turn it into a percentage, so we're going to multiply by 100%. Let's calculate the mass fraction of a saline solution where we're dividing 39.55 grams of salt in 1,000 grams of water. Now, you'll notice that I don't say what sort of salt it is. You might assume it's sodium chloride, but who knows? There's a lot of kinds of salt, right? It could be potassium chloride or something like that. It doesn't really matter what the thing is. What matters is the mass of the component. This is not related to moles at all. So the mass percent is going to be 39.55 grams divided by the total mass of the solution. So when I ask people to calculate this and they're not thinking, what they'll say is the total mass of solution is 1,000 grams. And they say that because that's how much water it is, right? When we did molality, we did the mass of the solvent. But this is the total mass of the solution. So that's water and salt, right? That's 1,000 grams plus 39.55 grams. So let's run that through our calculator, and what we get is 38.05%. The nice thing about using mass percent, as I said earlier, is that almost everything we throw into solution, we can weigh very easily. And so here, we're just using masses that we can easily measure. And so you'll see mass percent around a lot in real life. Right? Here's a picture I took when I was in the ER back in New York City. And let's zoom in on that IV bag, right? 0.9% sodium chloride. This is my saline solution there, keeping me hydrated. And of course, the doctor thought it was super funny that I was taking a picture of my saline solution bag. But, you know, what can you say? Nerd's gonna nerd. So mass percentages also get used for very, very small percentages, and it's really awkward to say this is 0.00006% by mass. So one thing that you will see around a lot is something that we call parts per million, where basically a ppm, a part per million, is 1/1,000,000th. Your component has 1/1,000,000th. For every million grams of solution, you're going to have 1 gram of your component. So if you're thinking about aqueous solutions in particular, you can have 1,000 grams of solution, which by the way is 1 liter, right? And your component will be 1 milligram of that. That's 1/1,000,000th of a liter. And so sometimes when you're talking about parts per million, you'll see things written as milligrams per liter. 1 milligram per liter is a part per million. Some things are even less concentrated than a part per million. And so you can have parts per billion. A part per billion is 1/1,000,000,000th of the mass of a solution. And in aqueous solution, that's going to be a microgram, 1 microgram in 1,000 grams, or we say a microgram per liter. And so where you're going to see this a lot is when you're talking about water quality. There are some things where you're not allowed to have more than a certain amount in parts per million of dissolved something. And there's things where you don't want to have more than X number of parts per billion in your drinking water. So for example, lead, I think it's like 10 or 15 parts per billion is the upper limit. Obviously, you don't want a lot of lead. You want a really, really tiny amount of lead in your drinking water. So we have a whole bunch of different concentration units. We use them at different times, but we're going to apply those in different ways as we move forward into our study of solutions. One thing you'll need to do is learn to convert between concentration units. I've linked to that video below. I hope this was helpful, and I will see you again soon.